what's up guys? Welcome to another episode of Numbers, the Letters of Math. As always, I am your host, Isaac Newton, and in this video, we're going to be taking a look at using the step and lsim functions to understand a step response to a first-order fluid system. So let's go take a look. We're waiting for our sponsorship from Coca-Cola to come through to hire more people for the graphics department. But in the meantime, in this graphic, what we have is a tank with a single input and output, flow resistance R, and area A. I won't bore you with the math, but we know that this will give us a first-order system whose ODE looks exactly like this. This isn't in standard form for a first-order ODE, I know, but for our purposes, that won't matter. So now that the math is done, let's go over to Matlab so that we can see what the results are from a step input. And so one of the things I like to do whenever I'm coding is use two little things called clear all and CLC. And so what it is that clear all does is that it allows me to just kind of wipe out all of the previous variables from my previous run so that they don't bleed over into the next thing. And so if I'm changing what variables are there or their values, there aren't any issues with that just because clear all clears them all out. And then CLC stands for clear command window. And so what clear command window does is down here in the command window, all the code from the previous running just kind of hangs out, but with CLC we can get rid of it. And so now we're going to go into our fluid system. And so we're going to go ahead and create a comment, right? It says fluid system up there at the top. And then we'll come down here, and the first thing that we're going to do is add our system constants. And so this shouldn't come as a surprise to anyone that gravity is still 9.81 meters per second squared. And then we have rho, our density of water, which is equal to 1,000 because we have water in the tank. And then the area of our tank. And then we're just going to set A and R, the resistance in the tank, equal to 1, and we can play with those variables later if we want. And then our inflow rate. This is important. This is the input to our system, and we're going to say that it's equal to 10. And so one thing to talk about is these semicolons. We know that in code, oftentimes that you'll put a semicolon at the end of the line or it won't run. Well, that isn't the case in Matlab. Whenever you have a line without a semicolon, you can see the equal sign is highlighted. And so what that means is that when we run the code without a semicolon, any lines that don't have a semicolon are going to go down into the command window. And so that's the only difference it makes. All of this code will still run perfectly fine, but we just want to, again, keep that command window clean, and so we'll add the semicolon on the end of each line. So let's go ahead and start coding. First thing we're going to do is we're going to define our transfer function, and so we're going to start with a little heading there. It says transfer function, and what that's going to do is going to describe our system to Matlab. And so we're going to start doing that by creating this variable sys, right? It's just any old variable, and we're going to use the function tf in order to help describe it. And so if you ever need help figuring out what a variable requires for its parameters or what it takes, come down here and type help in the command window and then the variable name. And when you click enter, what's going to happen is you're going to get all this information on everything that the thing can possibly do. And so we're going to scroll back up to the top, and we're looking for a specific use for this variable tf. And basically what it was is we pass it two vectors, a numerator and denominator, and what that will do is that is going to kind of describe the numerator and denominator of our transfer function. And so let's go back up here to the top, and we're going to start with our numerator. And for this system, it's a first order ODE, and so we're just going to click 1. It just has a numerator of 1. And then for the denominator, it's going to have two portions, right? The coefficient for the s and the coefficient for the constant. And so for our s coefficient, it's just going to be rho times a. And then for our other coefficient, the constant coefficient, it's just going to be g times rho over r. And so the next thing that we're going to be doing is using this step function that we have to analyze the system and see what a step input will do to it. And so before we put anything into this step function, we're going to go down and put help step and figure out exactly what it needs. And so we go ahead and scroll back up, and right here at the top is our first use. And what we do is we pass it the sys, which is kind of our transfer function, and then it's going to spit out the y value, which is the response, and then the time variable that corresponds to it. And so remember that our input, though, is 10. It's not just 1, and that's what we have in our transfer function is just a value of 1. So we can multiply our system variable times QMI like this, or we could add a 0 into that numerator, so it's a 10, and either way you get the same result. But we just have to make sure the input that we're giving to our system is accounted for inside of this step function right here. Now, notice that we're leaving the semicolon off of this line. That's because we want the output to be displayed. So we're going to go ahead and run it. And here it is in all of its mathematical glory. Let's take a moment to admire it. Well, anyway, I think we can do better. And so let's go ahead and add some labels and things onto it to make it the graph more readable and more clearly understood. And so what we're going to do is we're going to go down here and we're going to go ahead and put on some labels. This is our x-axis label, and we're going to label that time because that's what it is. And we're going to put the semicolon and do it all in one line. Here's our y label, and that's going to be height in tank. And then finally a title for our graph. And so that'll be our solved using step. And so that way we'll be able to differentiate between this one and the plot that we're going to make later. And so let's go up here and run it and see what it looks like. And here it is, and that looks much better. And so we can see our title up at the top, and then down on the x-axis we have time in seconds, and then the height of the tank on the y-axis, which is our response. And there's no units on that, so that's probably about 80 points off. But it's just going to share the units of what we defined in our system constants, and so it can be whatever you imagine, and so we'll call it gigameters just because. And so let's go ahead and keep going. Next thing we're going to be doing is using the lsim function, and so we're going to use our handy dandy trick that we learned earlier. We're going to come down here, and we're going to type lsim, and then remember to type help, and then click enter, and then so we can scroll right back up. And so we're going to be using the first version of this else system, which is going to take 3 vectors. Our system, a u, which is our input signal. As you can see right there, input signal described by u. And then t is our time, the time vector. And so what we're going to need to do is create all of those because we already have sys, but we need time first. There's 2 ways to do this. And so we're going to use a function called linspace first. And so we'll start by putting in our starting point, our ending point, and then the third parameter that linspace takes is the number of points we want in between. And so we're just going to say 100 because that's a nice round number. But you'll notice that that'll take some weird math if we want to know the spacing between the elements. So let's get rid of this for just a second, and we can do this another way. We have our starting point again, which is 0. And then we're going to go by steps of 0.01 all the way up to 1. 2 ways of defining a vector between 0 and 1. And so now we're going to work on this u guy, which is our input. We'll start him off by writing this line of code that says zeros, length t, comma 1. And so there's a lot going on here, so let's take a second to break it down and kind of explain it. First we have this function zeros, and so what this is going to do is it's going to create a vector of a given columns and rows, and it's just going to fill the whole thing with zeros. And so length t is the length of our vector t. And then we have the 1, which is just one column, because that's all we have for this input vector. And so now that we have all this put together, we're going to run it to just kind of save those things and make sure nothing has gone wrong. And thank goodness it hasn't. And so we're going to go ahead and see what this u is. As you can see, it has length t number of rows and then a single column going all the way up, and the whole thing's filled with zeros. And so now, next thing we're going to do is come down here and fill it with tens, because it's not actually, our input isn't just 0, it's filled with tens. And we're going to put those tens in there using a for loop, which is pretty much the same as it is in most other languages. We'll have index variable that starts at 0. It's going to increment by 1 until it gets to length t, which just so happens to be the number of columns we have in u. And for this for loop, we're going to start with the end, like we're reading a manga incorrectly, and then on the inside, hit the code to fill our input vector. And so how we're going to do that is we're going to say ux is equal to, and what we're doing here is we're going to be indexing this vector u, which initially is filled with zeros, and remember our x is our index variable, which is going to start 0 and increment by 1, and we're going to say it's equal to qmi. And so it's just going to, as it goes through the for loop, it's going to fill u with all those spots. And so we'll run the code, and it doesn't work. Even when you're creating a video and you have the power to cut out whatever you want, you still get errors in your code. Tell it like it is, folks. And so we're just going to do some quick editing right here, which was actually done a long time ago as I record this. And we're going to remember that you always index at 1 when you start out with a vector in Matlab. And so we run it again, and there she blows. Perfect. And so we'll come down here, and u is equal to 10. And so we filled everything with the input. And so what's cool about this is if the input were changing over time, we would be able to fill in this vector accordingly. Now we can use all this cool stuff we made. So y is equal to lsim And then we're going to put in our system, we're going to put in u, our input, and we're going to put in t, the time variable that corresponds to it. And so we'll go down here, and you'll notice lsim isn't going to put up a plot automatically, so we'll just plot t versus y. And so this is going to give us the plot of our step response. So we'll come up here, and we'll run the code. And there it is, but now it's even less readable than it was before. So let's go ahead and go back into our code like we did before and add some labels. And so we'll go down here, and we're going to start with our X label, and we're going to label it time, just like it is. And then our Y label, and that will be our height in the tank. And then finally a title. And so we'll throw on our title, and the title will be solved using lsim so that we can differentiate our two. And so you might have the question, why didn't the other plot show up when we ran the code? Well, that's a great question, because as you can see, we have our step and we have our plot, and both should spit out plots, but we need to add this figure on the top. This figure kind of saves each figure that the code tries to spit out, and so instead of just spitting out the last one, it's going to spit out every single one that we need to see. So let's run it, and there they both are at the same time, using that figure method. And so we can just take a look at it and see that both of the plots are essentially the same. We have our height in the tank as it goes up from 0 and peaks kind of at 1 times 10 to the minus 3. And this is the response we expected. There's no oscillation because it's a first order system and both of our responses are identical, and it peaks at a number that is reasonable. And there you have it. It looks like we're just about done. We were able to find the step response to a system that we defined using the transfer function, and then we applied that to the step function and the lsim function to generate plots, and both of them kind of gave us the correct answer, it seems. And so good job, everyone. Well done. And thank you so much for watching, and stay tuned while we continue to analyze these fluid systems and other systems using Matlab and Simulink.